Hi guys, this is Mrs. Allison. So you should have your notes sheets that says notes graphing sine and cosine. That's what we're going to look at today. This week we're going to focus on some of the basics of graphing, and then next week we'll work on translations of graphing, which will mimic all the graphs that we've done in the past. So let's get started on some basics. We're going to really today look at the parent functions and then two aspects that get changed with sine and cosine graphs. But there is some slightly different terminology that we use for sine and cosine graphs. So first let's define what these graphs look like. All right, so sine and cosine graphs are what we call periodic functions. Okay, what that means is a periodic function is a function that returns to the same value. I don't have big enough lines on here. At regular intervals. Okay, so it returns to the same value over and over again. At regular intervals. So it's not like it's a random time. It's very specific as to how it goes back to the values. And we're going to look at that in a moment when we graph these problems, especially the parent function. But it returns to the same value at regular intervals. Okay. The next thing that we want to talk about is what we call amplitude. Sine and cosine functions have what we call amplitude, and the amplitude, it's kind of funny because the next two definitions really go hand in hand. The amplitude is the distance from what we'll call the midline, and we're going to use the midline a lot, especially as we transform the graphs. That's midline, to the max or the min. Okay, and then the midline, because we use that word there, is the horizontal line that is halfway between the max and the min. So halfway between the maximum value and the minimum value. So it's halfway between the max and the min. Okay. And then we have something, we said it was called a periodic function. That's because each of our sine and cosine graphs have what we call a period. And the period of the sine and cosine graphs is the horizontal length. Horizontal length of one cycle. And what that means is it's how long it takes before the pattern repeats. So since it's a periodic function and it returns to the same value, how long until it returns to the same set of values? That's the period. So let's write that. Let's write how long until it returns to the same value. And we'll look at that in just a moment. Okay, so let's go to the next page, or the next section. Okay, so let's look at the parent function. So we're going to call this a parent function. And this is the parent function for all sine graphs. And our parent function is y equals sine of theta. That could say sine of x. Theta is just typically the notation we use for angles when we don't know the angles. And I've put a unit circle here, and you have one on your notes just to reference, because everything is based off of the unit circle. So the values that we get for the graph are all based off of the unit circle. Now I have a table of values here. I'm a little nervous about trying to write with my finger on an iPad into this table of values, so it may get messy real quick. We'll see what it looks like. You may just have to look at the completed version, which I have on the next slide. So I want to show you where the table of values come from. And then we're going to look at really only 5 of these points, which is kind of crazy because right now there's a lot of them. We're going to look at 5 of these points to be able to graph. Okay, so remember that the sign, when we talk ordered pairs on the unit circle, remember the sign is equivalent to y. I know this says y, but really this y here on our parent function could have been written f of x, or f of theta would have been at that point. So it's not the same y. When we're talking about the ordered pairs, remember that the ordered pairs go in the order cosine, then sine. So it's like x and then y. It's alphabetical just like x, y is. So let's look at the y values along the unit circle. So if I have my theta is 0, meaning I don't have any angle, this is where theta is 0, and the y value here is 0. Okay, so if we look at the y value being 0, is 0, 0. Okay, let's move on. Pi over 6. Pi over 6 is this angle, and if I look at the y value, I get 1/2. So I have 1/2. And I'm going to keep going around the circle. So if you would like, take a second and see if you get the same table of values as I do. Hit pause and then come back. But here's what happens. When I go through here, pi over 4, I get root 2 over 2. So I'm going to write root 2 over 2. Root 3, if I look, pi over 3, I get root 3 over 2. So I'm going to have root 3 over 2. Oops, yeah, see, that's hard to... Let's see if I can make that look a little bit more like a 3. Okay, and when I look at pi over 2, the y value is 1. 2 pi over 3, I've got positive root 3 over 2, and the signs are important. 3 pi over 4, I get root 2 over 2. 5 pi over 6, the y value is 1/2. Pi, the y value is 0. 7 pi over 6 is negative 1/2. 5 pi over 4, we get negative root 2 over 2. 4 pi over 3, we get negative root 3 over 2. That doesn't really look like a 3 either. 3 pi over 2, we get negative 1. 5 pi over 3, we get negative root 3 over 2. 7 pi over 4, we get negative root 2 over 2. 11 pi over 6, we get negative 1/2. And 2 pi, we get 0. And then if I were to keep going around the unit circle again, notice my values start over. So it was 0, positive 1/2, root 3 over 2. It would just keep going around the unit circle. So what I know is that this distance from 0 to 2 pi represents one period or one cycle. Okay, so this is what we look at when we talk about it being a periodic function. It takes it 0 to 2 pi before it starts repeating again. Now we are going to move on to the graph. So you can see I have the table of values filled out here, and we're going to look at what's called one fundamental period. What that means is it's really just one cycle through that starts as close to 0 as possible, assuming it hasn't been shifted left, right, up, or down, and we're not shifting this graph just yet. Okay, so let's look at, there's 5 points that we're really going to focus on, okay? We're going to focus on 0, 0, pi over 2, 1, pi, 0, 3 pi over 2, negative 1, 2 pi, 0. So I'm going to plot those 5 points, okay? 0, 0, let's see how this works on that. 0, 0, pi over 2, 1. We should probably label our axes. Let's do that. Okay, so we're going to call this, let's call this 1, so that this is 1/2, and then negative 1, so we have 1/2 here. That does say 1/2, believe it or not. And then negative 1/2 here. Didn't get better. Okay, so let's go back and graph. I was graphing in red. Pi over 2 is going to be 1. Pi is going to be 0. 3 pi over 2 is going to be negative 1. 2 pi is going to be 0. And if I were to continue, I would repeat those patterns again. Now, do I need to graph these other points in here? No, I don't need to once I'm used to what I'm graphing. But let's look at how they help shape what my graph should look like. So for example, I know where 1/2 is, so I'm going to go ahead and graph pi over 6 is 1/2. Now let's look at this graph and how it's broken up. This says pi over 2, this says pi, this says 3 pi over 2, this says 2 pi. But then in between there, it's divided into thirds, which means that this value here, let's go back to black, this value here is really pi over 6. This value here would be pi over 3. And then pi over 4 would be somewhere in the middle there, is where that pi over 4, because pi over 4 is halfway between 0 and pi over 2. So pi over 4 would be somewhere in the middle here. Okay, so let's look at what that looks like when I go to graph. Okay, so if I look at this next point, if I look at pi over 6, 1/2, pi over 6 is, oops, gotta go back to the pencil. Pi over 6 is this problem right here, point right here. And if I keep going, and I look at, say, for example, root 2 over 2. Well, I don't actually know what root 2 over 2 is. If I type it in my calculator, the decimal approximation is like 0.7. So if I look at that on the graph, it would be somewhere like 0.7. I'll color right there. And then pi over 3 is root 3 over 2. And again, I don't know that number off the top of my head, but if I type it in my calculator, we get root 3 over 2, and the decimal approximation is like 0.86. Okay, and what you'll see is then that pattern, I'm not sure where I just graphed that. That should be right here. And then if I repeat that pattern, I get something that looks like this. And then going backwards, I get something that looks like this. And then we're going backwards again. And my graph looks like this. So when I sketch this, I have a nice smooth, let's see if I can, curve through my points. This is what we call a cyclical graph, or a periodic function. Okay, now let's go back to those definitions, because there's a couple things I want to point out. One, we have the amplitude, which is the distance from the midline to the max or the min. The midline is the horizontal line halfway between the max and the min. So if I start there, my midline, in this case, in the parent function, is the x-axis, the line y equals 0. And then my amplitude is the distance between the midline to the max, or between the midline to the min. So in this problem, I have an amplitude of 1. Okay, so my amplitude is 1. And then I know that we talked about before that I have one period that takes from 0 to 2 pi. So when we write that down, we say that our period of this graph is 2 pi. Okay, and then the domain, let's talk about domain and range, because the domain and range are a little bit interesting. In this particular problem, the domain is going to be all reals. In fact, so it is in the cosine, because this graph keeps going on forever in both directions. There's no x value I can't plug in. But the range is pretty small. In this particular problem, the range goes from -1 to 1. Okay, So remember how I said we want to focus on these 5 points, right? The sine function of these 5 points, and I'm just going to highlight them on here, follows a pattern that I think will help us when we go to graph, and we'll look at it in a minute. But this pattern is middle, high. I'm going to write it down here. Middle, high, middle, low, middle. All sine functions repeat that pattern. Middle, high, middle, low, middle. You'll notice that the graph starts at the midline, goes to the highest point possible, goes back to the midline, goes to the lowest point possible, and then back to the midline. Okay, so that's the sine function. Now, let's look at what the cosine function and how it looks a little different. Okay, so let's look at the cosine graph because it follows some of the same patterns, but it looks a little different. So let's see what it looks like. So we're going to start by filling out the table of values, and the table of values again come from where the x values in this case, since this is our parent function and cosine represents the x values, we're going to fill out what the x values look like. So here we go. Starting with 0, the x value at 0 is 1. The x value at pi over 6 is root 3 over 2. The x value at pi over 4 is root 2 over 2. At pi over 3 is 1/2. At pi over 2 is 0. 2 pi over 3 is negative 1/2. Root 3 over 4 is negative root 2 over 2. 5 pi over 6 is negative root 3 over 2. Pi is negative 1. So you can see how the numbers are the same. They just go in a different order from the sign. Okay, so 7 pi over 6, we've got negative root 3 over 2. Negative root 2 over 2 for 5 pi over 4. Negative 1/2. 0. 1/2. Root 2 over 2. Root 3 over 2. And then back to 2 pi is 1. And if we were to go on any further, we would continue the pattern that we already started. You will notice again, just like before, that one period for the cosine graph is also 2 pi. This is going to be very important in a little bit when we start to change the function. And so let's move on and look at how this graph is similar yet different from the sine graph. Okay, so you can see that I've left the table of values. I've just typed them in. And now we're going to look at what this graph looks like. So let's label this graph ahead of time instead of last time. So we will call that one this negative 1. So this middle line here would be 1/2 or negative 1/2. You'll notice that this is a specific trig graph paper that goes from 0 to 2 pi. And so that makes it really nice. And again, there's 5 points that we're going to focus on. 0, pi over 2, pi, 3 pi over 2, and 2 pi. You'll notice it's the same points, same x values or theta values, but in this case, they actually have different y values. So let's look at what those look like. If I plot those 5 points, 0, 1, there's a point right there, pi over 2 zeros right here, pi negative 1's right here, 3 pi over 2 zeros here, and 2 pi is here. Okay, so this one looks different, and this one is a little bit easy to get wrong just because it doesn't follow quite the same pattern when we don't continue the graph on. So let's look at how those other x values, other theta values rather, play into this graph and help us. Okay, so we know root 3 over 2 from before is like 0.86, and we know that the way these are broken up is that this first tick mark is pi over 6, then pi over 3, and pi over 4 somewhere in the middle. Okay, so let's graph that. So at pi over 6, we have root 3 over 2, which is like 0.86. And then pi over 4 is 0.7. And then 0.5 for pi over 3. And then negative 0.5. And I'm just going to quickly go through these points. You could plot all of them if we look. And you can start to see the shape of this graph. And you're going to draw this with a nice smooth curve. And what do you notice? It looks just like my sine graph. It's just been moved. It's been shifted. And that's exactly what it is. If we were to continue this on, and I'm going to show you a picture in just a second that's not on your notes, but I just want to show you. If we continue this on, what you're going to see is that these two graphs look identical. We just have to know where to start to know which graph we're looking at, whether we're looking at sine or cosine. Okay, so a few key points again. First of all, the midline is still, in these problems, in my parent function, is still the x-axis, or y equals 0. The amplitude from the midline to the low or the midline to the high, you could go either side really, is still 1. So I'm going to write that. And sometimes we abbreviate amplitude as just AMP. So if you see that on any of the sheets, that is amplitude. So the amplitude is 1. And the period, remember the period is how long it takes it to complete a cycle before it starts back over. And the period here is still going to be 2 pi. So the period here is 2 pi. Okay, so let's talk domain and range. Did my domain change? No, my domain is still all reals. And my range, look at that, is still the exact same. So it's kind of nice. You don't actually have to, that's -1 to 1. You don't actually have to remember any different domain or range between the sine or the cosine, which is kind of nice. Okay, now I said again that there were 5 key points we're going to remember. Both graphs have 5 points that we really want to look at. And the pattern for this one, you'll notice it starts high, then goes to the middle, then goes low, then goes to the middle, then goes high. High, middle, low, middle, high. And if you can repeat that and you know that's for cosine, it makes it really easy to sketch graphs. Okay, questions so far? If you have any, write them down. Rewind the video, pause it if you need to. Go back and watch these parts because we're going to add in some shifts and some changes to the sine and cosine, the parent functions, and see how it affects our graph. Okay, so we're going to extend the idea of just the parent functions of sine and cosine, and we're going to add 2 changes, 2 transformations to them. And what you'll notice is that the 2 transformations we're adding is the A and the B. And it looks the same whether we're dealing with sine or cosine. And actually, really, we go through the process the same whether it's sine or cosine. It's just whether we start and do high, middle, low, high for cosine, or we do middle, high, middle, low, middle for sine. So, and I'll show you that in the next video when we look at examples. But I want to give you some, what these A and the B represent, okay? In these 2 problems, in both of these, my amplitude, it's kind of nice, it matches, is the absolute value of A. We say the absolute value because A can be negative, but the amplitude is a distance. It's the distance from the midline to the max, or the distance from the midline to the minimum. And so we know distance is never negative. We will have to pay attention to the negative, so we'll talk about that in the next video. But just so you know, the amplitude is the absolute value of A. And then the period we said in the parent functions was 2 pi, but the period is going to be 2 pi divided by the absolute value of B. That changes how far my graph goes. So the period, think of it like a horizontal stretch or shrink. Like, does it expand it? Does it make it take longer to complete one cycle, or is it shorter? Okay, so amplitude and period. Amplitude is the absolute value of A. the period is 2 pi divided by the absolute value of b. Most of the time, our b value is going to be positive. But in case it's not, those are our values. Now, I didn't want to make this video super long, so if you want to take a break, this would be a good time to do that before you start the second video and we look at some examples of sine and cosine. So, we'll see you in the next video.